Hello student, in this video I'm going to discuss more about audio digitization and compressing technique. Starting with to get audio or video in a computer, we must digitize it. Audio signals are continuous in time and amplitude. Audio signal must be digitized in both time and amplitude to be represented in a binary form. So try to understand this line, that is audio signal must be digitized the both time and amplitude to be represented in a binary form. So suppose this is the voice. Okay, it is in sinusoidal form. You will obviously need to use a converter, that is analog to digital, to create this waveform or digital waveform or pulse code modulations. To decide how to digitize audio data, we need to answer the following questions. What is the sampling rate? How finely is the data to be quantized? And is the quantization uniform? How is the audio data is formatted? So from the human perception, we know that vowels and bass sounds are low frequencies and consonants are high frequencies. So that is why speech is a complex waveform, because we speak mixing out vowels and consonant usually. So that is why that mixing of the frequencies are too much, like we are mixing the low frequencies with the high frequencies every time. Human most sensitive to low frequencies, so our human ear more sensitive to low frequencies. Most important region is 2 kilohertz to 4 kilohertz of frequencies. Hearing dependent on room and environment. Our hearing also dependent on the room and the environment. Sound masked by overlapping sounds. So any sound wave can be overlapped by other sound waves, which might be that overlapping might be in temporal means time domain, or in case of frequency domain also. Here you can see the step 1 of digitization is that sampling. Divide the horizontal axis time dimension into discrete pieces. Uniform sampling is ubiquitous everywhere at once. Here you can see original analog signal is sampled by putting horizontal axis in the time dimension into discrete pieces. Sample signal is rendered for playback. So in case of sampling, one very popular theorem can be used, or people talks about this theorem, that is Nyquist theorem. Suppose we are sampling a waveform, then how often do we need to sample it to figure out its frequency? So that is a very big question. Suppose we are sampling a waveform, then our main question is that how often or how much do we need to sample it to figure out its actual frequency. Signals can be decomposed or sampled into sum of sinusoids, means in parts of sinusoids. The Nyquist theorem states that how frequently we must sample in time to be able to recover the original sound, means we must sample frequently in time so that we can recover the original sound. So Nyquist theorem, also known as sampling theorem, is a principle that engineers follow in the digitization of analog signals. For analog to digital conversion (ADC) to result in a faithful reproduction of the signals, slices called samples of the analog waveform must be taken frequently, means at very brief amount of time. The numbers of samples per second is called sampling rate or sampling frequency. So if you here you can see it can be proven that bandwidth limited signal can be fully reconstructed from its sample if the sample rate is at least twice the highest frequency in a signal. So what it is saying, if you are sampling the actual frequency at a rate which is twice than the highest frequency in the signal, then you can directly fully reconstruct the original signal. So here in this figure you can see this is the original waveform. If you sample that in one frequency, one of the original frequency f, then you can get this one. So to reconstruct this signal to this one, you might not get the original one because these are divided at that sample size. So those points or those discrete points will be taken while taken for digitizing. So having those points only might not be enough to create the original signal. But if you sample at twice f, then might be, or it might be possible to create, because you can see this is a zigzag pattern which is almost similar to the original frequency, or we can recover the original frequency if you sample that thing in twice f or twice f of the twice of the original frequency. But if you also can go for more than twice of, like if you sample it 10 f frequency, means within that range there are 10 between one frequency, suppose 1 2 3 4 5 6 7 8 9 10. So there are 10 samples in that one sinusoidal wave. So having that 10 times of original frequency, obviously you will get the original frequency, or you can recover the original frequency, reconstruct the original frequency. So higher the sampling rate, higher the possibility of creating the original sound wave. So obviously in the computer we are going to store in the digital values at which you are sampling. So if you store in lower sampling rate, then obviously it will be tough to reconstruct the original frequency because you will have lower numbers of informations. Step 2, that is quantization, converts actual amplitude samples values into an integer approximation. So in case of quantization, it converts actual amplitude samples values, usually voltage measurements, into integer approximation. So in case of quantization, it actually converts the amplitude value into the actual or integer approximation. Trade-off between number of bits required and error. So there would be a trade-off between the number of bits required to store that value and what is the error in case of you are storing that actual amplitude value in an approximation value. So there will be some trade-off. So human perception limitations affect allowable error. So when we hear the sound generated from the computer or the sound which is already stored in a computer, we might not exactly differentiate that error. So that is why it is saying that human perception limitations affect allowable error. Specification applications affects allowable error also. So application or software specifications also affect some allowable error. Once samples have been captured discrete in time by sampling Nyquist, they must be made discrete in amplitude by quantization. So after getting the sample size, you need to measure the amplitude which need to be quantized. That is the step. Two approach for quantization. It might be rounding the sample to closest integer. Suppose if the actual amplitude value is 3.14, then you can round it to quantized value, that is 3. Or create a quantizer table that generates a staircase pattern of values based on a step size. Or rather than rounding of the value, you can create a different sort of table so that you can map the actual amplitude value, that stepwise value, to create a pattern of values which will create a step value or step of quantized value, which will be more important to create or reconstruct the original wave. Analog to, so this is the quantization step. The third one, reconstruction. Analog to digital converter provides a sampled and quantized binary code, and in other hand, digital to analog converter converts that quantized binary code back into approximation of the analog signal. Reverse the quantization process. Mean whatever you have quantized, that need to be revert back to the amplitude level, and also reconstruct the wave by joining those amplitude levels, by clocking the code to the as same sample rate as the ADC conversion. After quantization, some information is lost. So obviously when you quantize something, when you quantize an amplitude value, some value will be lost or some information might be lost. Errors introduced. The difference between the original sample value and the rounded value is called quantization error. And a signal to noise ratio is the ratio of relative sizes of the signal values and the error. The higher the SNR, the smaller the average error is with respect to the signal value, and the better the fidelity. So we'll try to understand this part. Here you can see this is the sinusoidal wave. This is vertical partition, or you can say sample partition, sampling interval. Okay, so here you can see for higher the values of suppose sampling signal level 11.6, that is 11.6, this is 11.8, this is 12.1, 12.6, 14.1, sample signal level 15.3, like that in time. And quantization level is this is the quantization level, means this is almost that amplitude level. Sampling level is the time level 11.6, this is 0.2, that is the interval. 11.6 0.2 plus 0.2, that is 11.8 plus 0.3, that is 12.1, almost that interval. So it is the time value. This is the quantized level, this is the amplitude level. So quantization error is actually, so here you can see 11.6 is this 11.6, and actually in the quantization level you create is 12. For 11.8 you are creating 12, for 12.1 you are creating 12, 12.6 you are creating 13. So quantization error is the difference between these two levels. So bit sequence for 12 is 0 1 1 0 0 to demonstrate 12 value. For 12 this is also 0 1 1 0 0. So like that it will create the bit sequence for this quantization level, but there will be some error related to it. So that is how the audio is sampled and quantized. Non-uniform quantizer, difficult to make and expensive. Means if you can build a non-uniform quantizers, it is difficult to make and expensive. Solution is that compending, or you can say uniform Q, or then first apply the compending, then provide uniform quantization, then expand. Here xn is a speech or a song, or like this. Yn is compounded signal. This is a function, compounding function. Segment of xn is this part, close view of this signal, this part. Segment of yn, compounded signal. So it is actually, you can see the difference between these two signal. This is the original signal, but this is the compounded signal. Okay, so here you can see the actual difference between these two. So this is called compounding. So yn, that compounding function, is actually some function x of n. So here x max, so here you can see this is red line is non-compounding. Using mu law or a law, we can do different type of compounding. This is mu law quantized, that is mu law quantized, okay, and that is a law quantized. So this is a linear signal decimal values and encoded signal decimal values. So x max log of plus mu of xn by x max log of 1 plus mu dot sine of xn. So this is some part that is used to create non-uniform quantizers. This is not so much important in your case, but try to go through this for more understanding. Okay, next we are going for the audio and sound compression techniques. So we'll try to understand this part in next video. So till then, if you have any doubt or questions, please let me know. Thank you.